move on to the next section, and this is about what happens when we allow the basic state flow to become more interesting, okay, more complicated. So up to now we've assumed that the basic state flow is just these uniform westerlies, and we've got our parcel which displaces, which creates a Rossby wave, right? Bless you. What happens now if we say that this flow is a kind of jet? So let's say we've got a sharp jet here in the westerlies, right? And I've drawn this so that you can see there's some shear in the flow here, right? So at this reference latitude, you can't say that the relative vorticity is 0 anymore. It's got a kind of anti-clockwise. If you drop a wheel into this flow, it'll go around anti-clockwise because of this shear, right? So you can see the vorticity is greater than 0 here, the relative vorticity. And you move it north, as before, right? And, well, F gets bigger. So if this thing is conserved, then you'd expect this relative vorticity to get smaller. Well, guess what? It does get smaller because of the way I've drawn the background flow. You've got more shear here down south than you have here up north. So it's quite possible for this to work without having to induce some kind of secondary circulation. Yeah? And so it can just go north and doesn't have to induce any curvature in the flow. It could even go the other way, right? So you've got something which is allowed to just take off, right? So you can see where I'm going with this. This is the beginnings of a consideration of instability. Right? Before we talk about instability, I just want to say one more thing about the consequences of having a more realistic background flow. So let's just talk about perturbations on the shear flow. We'll begin the theory part, right? So here are our momentum equations, and here's our continuity equation. We've got a beta approximation here, and we're going to try and find the appropriate vorticity equation, okay? But first we'll choose a background flow, all right? U bar of y, which is a solution of these equations, okay? So let's say it's a geostrophic background flow, okay? So we can substitute that into here, right? And then we add perturbations to these equations, u prime and v prime, okay? And we look for the linear vorticity equation. So the vorticity equation which is linear in perturbations about these flows. So you know how to find the vorticity equation, don't you? Just take the curl of these momentum equations. d by dx of one minus d by dy of the other one. And what you'll end up with is, again, a perturbation vorticity equation where you have one term where you have the advection of the perturbation by the basic state flow, and another term where they have the advection of the basic state absolute vorticity by the perturbation flow. The difference now, you see, is that we have meridional variations in the basic state flow. Okay, that's what we didn't have before. So yeah, here's the derivation of that vorticity equation. You don't have to do anything. I've done it all for you, right? These blue slides there, my present to you. So let's take that vorticity equation, and to start with, let's just try and find some Rossby waves, okay? So what we're going to do is, well, we find the dispersion relation, and it's the same as before, except we have now this relative vorticity associated with the background flow in the term. And what we're going to do is just, well, let's just say we're interested in stationary Rossby waves, okay? So Rossby waves with omega equals 0. Rossby waves which just stay in place. This is interesting to atmospheric scientists, atmospheric dynamicists. And so if we do that, that simplifies things. We just set omega equal to 0, and we see what is the relationship now between the properties of the wave, L squared and M squared, if you like, and the background flow, U. Right? We can get that out, and we end up with this wave number, K, which is given by this expression. So Ks, which is L squared plus M squared, is equal to beta minus d squared u by dy squared over u, right? And so that is our stationary wave number. So we want that to be real. If that exists, then we can have stationary waves. So this thing inside this square root has to be positive, otherwise we can't have stationary Rossby waves, right? And the properties of this thing will tell us about the propagation of the stationary Rossby waves. And so there's some pictures here. You can see there's the stationary Rossby wave number. Everywhere where it's white, that's where this thing is complex or imaginary. Okay, so that's where you can't have Rossby waves, stationary Rossby waves, or very low frequency Rossby waves going through these white regions. There's an important area in the Eastern Pacific where a Rossby wave can get through. That's the Pacific waveguide. And see, this is composed of the zonal wind and the meridional vorticity gradient. So, I mean, strictly speaking, this thing must have the same sign as this. So beta minus u, y must have the same sign as u. What that usually means is that u must be positive, right? So you must have westerlies. Otherwise, you can't have stationary Rossby waves in that region. And most of the tropics have easterlies apart from this part here. And you can, again, find the group speed of these Rossby waves. So d by dl and d by dm of the dispersion of omega gives you the group velocity, and you can again plot the different components of the group velocity to give you the direction of the Rossby wave, and you can trace these rays, which will give you an idea, a theoretical idea of where your Rossby waves are going to be situated. So that's stationary Rossby waves. Now let's get onto this idea that you've got a solution that can grow. So I showed you a parcel which can take off and just keep going, right? So whenever you talk about waves, the other side of the coin is to talk about instability. These wave solutions, these trigonometric solutions, are imaginary exponentials, e to the I, etc. Okay? And what if that thing, that etc., also has an imaginary part? Then you get a real exponential. So here, for example, e to the I omega t, that's an oscillation, right? What if omega has an imaginary component? Then it's e to the I times something real times t, so that's an exponential growth with time, okay? That is unstable. So it's the other, it's mathematically very similar, physically a very different thing. A gravity wave is stable. A thunderstorm is unstable, okay? A Rossby wave is stable, and this, barotropic instability, this leads to rapid development, in principle. So here's our, again, this is our vorticity equation. We're going to seek solutions of the type, now our coefficients are a function of latitude. That's what's different. We didn't do that before. It's very similar to what we did with the vertical dependence. Now, it's latitude dependence, okay? So again, if I substitute this into here, I won't get just an algebraic equation, I'll get a differential equation, an ordinary differential equation for phi, okay? And here it is, right? So I substitute this into here, I get this. This is called the Rayleigh equation. So if we want to analyze the instability, we have to deal with this Rayleigh equation. But we're not going to solve it. We're not going to try and find solutions to this Rayleigh equation. What we're going to do is analyze it for the possibility of growth. So for the possibility of exponential solutions here. Is it possible for omega to have an imaginary part? So we talk about our wave properties, if you like, having complex conjugate pairs associated with the solution. And so omega has a real part plus an imaginary part, and omega star will be the complex conjugate of that. And we suppose that the wave number L is real. You could say it was complex, but it wouldn't add anything. It would just be more mathematics, right? So let's just say L is real. It's represented as something which is in physical space. And omega over L, that's the phase speed. That can be complex because omega can be complex. So our phase speed C has a real part and an imaginary part. Now, what we're interested in is it possible for C to have an imaginary part? Because if it does, that means omega has an imaginary part, which means we have some real exponentials here, which means we have possibility of instability. Yeah? So we're going to analyze this equation for the possibility of C having an imaginary part. All right? And the procedure, so here, what is this? This is just the derivation of that Rayleigh equation, okay? You don't have to do anything. Usually when you read textbooks, you have to fill in a lot of gaps, right? I've done all the work for you. You don't know you're born. You're so lucky. Right. So here's the Rayleigh equation. What are we going to do to it? We're going to multiply it by the complex conjugate of phi and integrate it across the domain from 0 to L, applying boundary conditions to the north and south that phi equals 0. Okay? Well, integrate these two terms. Well, this term, integrate that, it's very straightforward. Phi times its complex conjugate is just the magnitude of phi squared times L squared. That doesn't change. This term here, this times the complex conjugate of phi will give you that if you integrate by parts. Once again, I show you that on a blue slide. Okay. So what we've got here in this first term is something which is positive, definite, and real. Everything inside that integral is positive and real, but this is negative, which means that this term must be positive. Also, if there's anything complex in this, if there's anything imaginary, it must be in this term, right? So is it possible that there's an imaginary part to this term? Well, how do we find that out? What we do is we multiply the top and the bottom by the complex conjugate of u bar minus c, because that's what we've got on the bottom. That gives us a real denominator, and on the outside of the integral we will have a u bar minus c. We don't care about the u bar part because we know that's real. We don't care about the real part of c because we know that's real. The only thing we care about is if there's an imaginary part to c, which will give us this term, right? This is now the imaginary part of that second term. Now, it has to be equal to 0 because it's the only imaginary bit of the whole equation, and the equation equates something to 0. So if this whole equation has got a real part and an imaginary part, they must separately both equal 0, right? So this must equal 0. How can this equal 0? Well, either Ci equals 0, which means there's no imaginary part to the phase speed and the thing is stable, or Ci is not 0, in which case the integral must be 0, right? So that's the necessary condition for having an imaginary part to the phase speed. This integral must be 0, all right? How can this integral be 0? Well, we know that this is real and positive. So it must be something to do with this part of the integrand, beta minus d squared u by dy squared. And we, at the very least, it's necessary for this term, well, either it's 0 everywhere, or if it's positive somewhere, it must be negative somewhere else. Okay? It must change sign somewhere in the domain. It must cross that 0 line somewhere in the domain between 0 and L. Okay? So what we have discovered then is that this term, which can be written like this, d by dy of the absolute vorticity of the background flow, must change sign somewhere in the domain. So this is a necessary condition for this integral to be 0, which is a necessary condition for this phase speed to have an imaginary part, which is a necessary condition for instability. So this is a necessary condition for instability. This is the Rayleigh criterion for instability. This must change sign somewhere in the domain, right? Which, another way of saying that is that you have to have an extremum. If the gradient changes sign somewhere in the domain, that means you've got either a maximum or a minimum, okay? An extremum. So the absolute vorticity must have either a maximum or a minimum somewhere in the domain. Okay, so that's one condition. That's the Rayleigh condition, the necessary condition for barotropic instability. There's another one. This is called the Fjørtoft condition. All right. So if we go back to our equation that we had before, and we know we've already dealt with the imaginary part, we know also that the real part must be satisfied, which means that this term on the right must be positive, because we know that's negative. Okay. Well, this term looks fairly similar to the one we already just dealt with, which we know must equal 0. It's just u bar minus cr, which is different, the real part of c. So that's the stuff which is left over The other bit was CI times the same thing, right? This is the real part, U bar minus CR. We know that must be positive, right? But if we just abstract that, and we're going to follow a little bit of logic here, Fjordtoft logic, all right? We have an integral, which is 0, all right? And so that's this, right? That's our Rayleigh condition. We have another integral, the same thing times u minus c, which is positive, all right? Now, we could write that a times u minus u naught is a times u minus c plus a times c minus u naught, right? That's just trivial, okay? Now we know that c is a constant and u naught is a constant, so this term here, by the Rayleigh condition, must be 0, which means that these two things are the same, which means that this thing must also, just like this thing, be positive, all right? So we've replaced the c with an arbitrary value u naught, which we have not defined. So that must mean that this must be true for any value of u naught. We can pick any value, it must be true, okay? So it makes it a bit more of a powerful criterion. So that means that if this integral here, with any value here, u bar minus u naught times this, which is beta minus d squared u bar dy squared, the gradient of the absolute vorticity, if this integral is to be positive, then this must be positive somewhere, right, in the domain. That's the absolute minimum, right? So it must be positive somewhere in the domain. This is the Fjordtoft criterion. And it must be true for all values of u naught. Right, so what can we pick for u naught? Let's say we pick something very, very, very big. So that means that this term is certainly negative, which means that, well, this has got to be negative somewhere in the domain. Effectively, all we've done is recover the Rayleigh criterion, because the Rayleigh criterion tells me it's got to have both signs in the domain. It says it's got to change sign in the domain. So if we're saying it's got to be negative somewhere, that's just a weaker version of saying it's got to change sign. Let's say we pick u naught very, very big and negative. Well, this has got to be positive somewhere. Again, it's got to have a sign somewhere, which is just a weaker way of saying it's got to have both signs. So large values of u naught add nothing to the Rayleigh criterion. But then what's critical, what's interesting, is that if u naught has a medium kind of value, so that this term also changes sign in the domain somewhere, well, then you add an extra criterion which is more of a constraint than just the Rayleigh criterion. So that's the Fjordtoft criterion. And these two criteria, remember, these two criteria are just necessary conditions. They are not sufficient conditions, right? So if one of these conditions is satisfied, and this is important to remember, right? So if you look at a vorticity map or a potential vorticity map, and you say, oh, there's a change of sign there in the gradient, right? Well, that doesn't tell you it's unstable. It just tells you that it's possible for it to be unstable. It's a necessary condition. If, on the other hand, you see that the condition is not satisfied, then you know it's stable, right? So the non-satisfaction of a necessary condition is a sufficient condition for stability. Right? That's just logic. Right, so let's have a look at some profiles. And start with this one, Poisson flow. It's the kind of flow you get in a viscous pipe. Quadratic form for U. So the gradient of the vorticity is just a constant. It can't change sign in the domain, therefore it must be stable. There's no extremum, okay? Gaussian jet, well, that's an exponential form, right? So yeah, it's got extrema, and therefore it could possibly be unstable. Sinusoidal flow, likewise, the derivative of sinusoidal function is another sinusoidal function, so it's always going to have extrema, possibly unstable. A polynomial, and it's obviously a third order polynomial because the second derivative is a linear function here. It's got boundary extrema, okay? So by the Rayleigh criterion, it could be unstable. It's got extremum here and here, okay, on the boundaries. But what you need is for this thing to have the same sign as minus this thing, for the thing to be positive, somewhere in the domain. And that's got to be true for all values of the constant u naught, right? So if you look at this, and then you look at minus that, then they've always got opposite signs, which means you've got the multiple of the 2 is never positive. So it fails the Fjørtoft criterion. Now, as I say, this U0 constant would shift this left and right. Okay? So you could shift it by defining a U0 to satisfy the Fjørtoft criterion, but that wouldn't work because it's got to be true for all values of U0. And in this case, it fails for U0 equals 0. The other thing to remember is that we haven't included beta in this. So all these profiles of vorticity gradients could be shifted as well by beta. So remember that. How does it work? How do things become barotropically unstable? Here's an example of a background flow where you have, to the south, you have easterlies, uniform easterlies. To the north, you have uniform westerlies. And in between, there's a transition zone where there's a shear. And this is a strip of vorticity, right? Values of vorticity. So yeah, there's no vorticity in the flow here, and there's no vorticity in the flow here, but in this region here, we have some vorticity. So we have negative vorticity in this shear here, because it's clockwise, okay? Imagine a small perturbation, so this streamline gets pushed a little bit to the north, right? And you have this clockwise flow here, and here, okay? Relative to the absence of rotational flow in the background, north and south of the strip. And then so you ask what happens next. Imagine this secondary circulation is going to displace these vorticity contours because it's a conservation relation, okay? And so this is going to go further south, this is going to go further north, this is going to go further south, and so the wiggle which has appeared on this vorticity contour is going to get amplified. Okay, it's going to get pushed further and further, and eventually, well, very quickly actually, it's going to roll up. This is linear, okay? This becomes non-linear very quickly, and so it wouldn't really be susceptible to our linear analysis, but it's the mechanism, the kind of advective, the vorticity advection by the secondary flow, which produces this amplification of the initial anomaly. So this is a computer simulation, right? This is a laboratory simulation, so they've taken some kind of flow in some kind of giant fish tank of some sort, and they've introduced a very well-controlled shear layer into the flow, and they just let it go. They maybe put a little perturbation, and it develops, you see, this perturbation, this wave, which turns into these vortices, right? It looks very much like the computer simulation. Right, so that's barotropic instability.